almost ready. 2 seconds.
We left off at the experience of witnessing every sphere in closest packing changing, becoming a space, and space becoming a sphere. We'd been through discovering what the shapes of spaces between the spheres were. They were concave, vector equilibrium, concave octahedron. And I'd pointed out to you that the vector equilibrium itself then could go convex or concave, and the spheres I see then as the convex forms. Remember, vector equilibrium is using the most space in the universe, and all the things happen by contracting, so that when its edges, vectors, became curved, they reached a lesser distance. So these spheres in closest packing are actually they produce what you call the isotropic vector matrix. The centers of each one are equidistant from one another, but it produces a isotropic vector matrix whose chord length, vector length, is a little less than the length of the vector equilibrium before all this starts. I think I'd pointed out to you that everything goes on inside the vector equilibrium. I'm convinced is what goes on within the nucleus. And everything that goes on outside the vector equilibrium is what goes on in chemistry, the associating of atoms into molecules. This is the internal affairs of the atom. Incidentally, just saying that World War I, I mentioned to you the other day, they had physics and there was something called electricity in addition to physics. Physics mostly mechanics. And after World War I, suddenly the electron became of the greatest importance. So physics was really electronics. And then World War II saw physics become nuclear physics. And we saw the physicists and the chemists then crossing lines with one another, and the chemists and the biologists crossing lines with one another. So that after World War II at MIT, they decided to have sorting this out, and they decided from there on that chemistry was now dealing with atoms, but the chemistry was dealing with external affairs of the atoms, and the physicists were dealing with internal affairs of the atoms. So the kind of things that go on inside my vector equilibrium, these contractions and so forth, I am assuming really are the internal affairs of the atom. And but I just want you all to remember then that as the vector equilibrium contracting, and it's contracting by virtue of its edges becoming either convex or concave. If they become concave, they become the spaces between the spheres. If they become convex, they become the spheres. And they occupy, the spheres then occupy, or the spaces occupy, the same positions if you had a complex of cubes, many cubes stacked up and layer after layer, all tightly packed. If you're looking at like a checkerboard, every other cube was black and then white, black and white. Then you would have the whites that would be the spaces, and the blacks would be the spheres. So when this transformation occurs, then the white then becomes the sphere and so forth. I want you to have that feeling about what's going on here quite strongly. And the model that I photographed made it possible to demonstrate that is still in existence in Cambridge, and someday we hope to have a better model made, fresh one today. In respect to our whole experience together and my starting and operating entirely spontaneously and finding my way in, not knowing just what I was going to say as we started. I have gradually found now what it is I have said, and I can remember all the things. We've now done approximately 20 hours, and now I can see, having done the 20 hours, I can really feel the things that I'm going to have to do in order to be able to be complete as we would like to be. I'm hoping I'll be able to do it in the available further 20 hours we have. That's all we have now. And means that I don't want to lose any more time at the beginnings of our evenings or ends as necessary. I am planning then for your questions, and I thought that the questions had best be the last day, because I'm sure there are many things you'll ask me that I would like to bring in. For instance, I've been asked very many questions about philosophy, about God, what I feel about such matters, and I plan to do that the next to last day. In other words, I'm beginning to see exactly what we have available and what we better do with that time. And I would like to also point out that I'm hoping that someday you'll all be interested enough in what we've experienced together to wish, for instance, to make models for on your own experience. Because with the video as a medium, video as a medium, it is possible, as with all tape, to come back at any point and actually run over that point and superimpose, takes out the old image and puts in the new. So we could keep the voice going and could put in a better picture of the model at various points as we see fit. If we're unhappy about what we have as a total result, I think it'll be primarily due to the feeling about models. One of the limitations of pictures and so forth is that I have large numbers of slides of really fairly high order, and but the machine that takes slides to project them into the video system, for some reason or other, has been designed to frame it with a smaller frame than the framing of the standard 35 millimeter slides, so that I keep losing very important information. And as I look at the pictures being shown, that I always got taken aback, and I lose a little enthusiasm for the picture side. But I want you to understand, because I said we must have the truth in it at all times, and this is the way it is, and I'm extraordinarily grateful that I live in a moment when it is possible to do what we're doing, the reality to make such a recording. So that I know everything, all the technology has its movements forward, and I'm sure this one will be improved in time, but we ourselves could, if we liked our product, could very greatly improve it by making models at various places that would be better than the picture we see there. Now I'm going to have some of these slides, please. And there are some that I'm going to do tonight that review fairly fast some of the things we've already been through the other night, but I think I found slides that seem to be a little better. And now you remember dealing with our topology, and we have this inventory of relative numbers of vertexes, faces, and edges, that when we took out the two polar or axial vertexes of every accounting, then we found that the relative abundance was such that for every vertex there were always two faces, there were always three edges, which told us then, because everything is double, there's an inside and out, so there's a multiplicative 2, there's 6 of the vectors. In this picture right now, we see on the tetrahedron, the left, there are three of the edges have been shadowed. I wanted to try to follow those three increments. You see in the cube 3 red ones and 3 black ones and 3 white ones. And there's one other color, but they're always in threes. And we see in the octahedron, next picture, You make any of the other polyhedra were always just in threes, and those threes, remember, also were, our friend, action, reaction, and resultant. So that the vectors are always action, reaction, resultant, and they always come together to make sum total structures. Next picture, please. This is one that I mentioned something to you the other day when it came to the three-frequency vector equilibrium made out of spheres, which shows four to an edge, four balls to an edge, but it's three spaces. I also mentioned that in the square faces of the vector equilibrium, where the outer shell was the number 92, there were in each of the square faces four spheres which could be loaned out of the system without in any way hurting the structure, the integrity of the structure of the system. And I find then we do find atoms in combination, combining chemistry, where they're able to loan, one can loan up to four out to the other. And we see that, those fourness in those square faces. Those square faces, you remember, were square half octahedron. We had them, they were the internal octahedra, where the two vector equilibria came face to face, and the octahedra is hidden in between. So that would be where the four could be exchanged to do the bonding between them. Next picture, please. Now here, you see it looks like a lot of circles. What I did was to take a metal floor in a subway where people all walking over it all the time, scratching. And there's a bright light. But at any rate, you'll find that if you look at any scratched surface, you'll always see circles. And you keep moving along, but there's a beautiful sun of circles every time. And it's very important to explain to yourself how all the randomness can disclose to you a set of circles, concentric circles. Well, it's fairly easy to realize that the shadows, as long as there's a light, the scratches actually have shadows. And like a mountain range, there's a dark side and there's a light side of the mountain range where the sun shines on it. And what happens here with the light present is that all the lines that are approximately at right angles or precessional to the light are the ones that get lit up. So you'll always find then the other ones don't get illuminated, so you always get then this beautiful sunburst. I find this a very important matter because it really shows how any kind of an event can find its own set of orders in a set of very great randomness. Next picture, please. Now we're looking at a sun shining on a spherical surface, very shiny one, had also been scratched, polished a lot. And you see there a star pattern. Not only is there the circles, but it makes into the hexagon. Breaks down into that. It sorts itself out in that no matter where you look. Next picture, please. Here I was studying the action-reaction. Several of the items in this picture are not there, but we have a man there's a rowboat, and he jumps from one rowboat to another, making one shoot very fast. But you find that the rowboat that he jumped out of and the one that goes forth, they both tended to really steer right around. They don't go off the next picture. And I'm trying to make that a little clearer, where he's now jumping from a boat to a little sloop and so forth, and you see the arrows down the bottom there indicate the way the thing happens. The barred line, the barber pole part, is where he's doing the jumping, and the white is the boat that he had jumped from, and the red is the one he jumped onto. Next picture. And we have the same business here again, where he's jumping from one to the other, and the barber pole is where he's doing the jumping, and the white is the one he jumped from, and the red is the one he jumped onto, and they come back. The triangle even comes back to itself. Next picture. So we find all these different ways in which the the three vectors of action, reaction, resultant, which are always in every system, can come out. They can look like a Z, or they can come back and even look like a triangle. It's fun to make them look like a triangle. And you can take two triangles like this, and you say, I have two triangles, and then you open them up and put the together, and you find they make the six edges of the tetrahedron. So suddenly you had two triangles you put in, and you come out with four triangles. In other words, there always is that invisible, as I give you the convex and concave, and the convex just has nothingness in it. Next picture. Now I'm going to look at two tetrahedra, and the white and the black tetrahedron. I made this model out of a very stout rod, and the white and black, and they congruent, and they're springy rods, and so they're able to sort of twist in and out of one another. Next picture, I find that I had one was locked into the other, so they can't get away, so they get to where they be just vertex to vertex like that. Next picture. Then they can be rotated in such a way that one is inside the other, and makes a star. They call this the 8-pointed star, which makes the cube. And it's a fascinating matter to find one of those tetrahedra can literally roll like as if it was a ball instead of a tetrahedron. The relationship of the edge to edge, no matter how you make it, they never get out of kilter. They have six edges always touching, and excuse me, yeah, six edges always touching six edges, and they're always in contact, and one never pushes or pulls. They rotate around in each other superbly, either be congruent or in this position. Next picture. Here's another one of the rotated positions. Next picture. Then they can, of course, be face to face, the two tetra. And this, I remember, was the atom clock, where they pump, when the one vertex would pump through the base and come out the other side, back and forth, back and forth. Next picture. Now, I'm going to do things, give you some information that I hope is going to help to understand and, of course, and feel quite strongly the model of yesterday when we saw the spaces becoming the spheres and spheres becoming the spaces, and the transformation from being vector equilibrium to octahedron and so forth. Now, here is a tetrahedron inside of a cube, giving the cube its shape. And I have also strung on the top of the cube a single string that goes from the far right corner back to the far left corner, and then back to the center. It's a circle, and it's strung over the pipes. And the edge of the tetrahedron is just lying between the paired circle of these two lines. And then we have a string, but you can't really see, at the middle of the top edge of the tetrahedron, and we're going to pull the tetrahedron out of the cube. Next picture. We're starting to lift the tetrahedron. It slides with its vertex to follow beautifully the edges, and we find the six edges keep sliding absolutely perfectly on the four square edges of the cube at the top. As we pull it up, that line which I said went back and forth from left corner to right corner, it went under the thing, back over the top, over the top. It makes it now as a quadrangle, and as we're pulling the tetrahedron out, it gets spread. Next picture. Now the tetrahedron has been pulled a little further, and you can see the line which I said, this piece of rope that goes around, that quadrangle is opening up all the time. And all the time, all the parts of the tetrahedron are touching the cube very beautifully, sliding right out. Next picture. Now it's halfway out, and the straight piece of rope has become a square. And that square, incidentally, is what has a cross-section of a tetrahedron. If you want to make it really good, you cut right here, and the cut right comes out here, and you find that is where the octahedron is, inside the section of the octahedron. And so, next picture, please. Now the tetrahedron is being pulled a little further, and the quadrangle is now contracting from a square, but is now orienting from another corner. Next picture. It's oriented at 90 degrees. This is one of those precessional things. It went from going this way to that way now. Next picture. Now I guess we're ready to be pulled out. Next picture. And the rope goes absolutely right straight across now. And next picture. And then the cube, take the tetrahedron out and the cube collapses. It's a very beautiful model of this one we made for Institute of Design in Chicago long years ago. Now, this picture, I'm sorry to say, does not show it very clearly, but you'll see a cube. There's three cubes, one above the other. And in that cube, you'll find that there is a position where a triangle inside the cube sits near the lower right-hand side. In the top picture, that triangle is in there. It's actually following position. Remember, I had a tetrahedron inside the cube, and it's taking one of the faces of that tetrahedron going up like this and back. So it's inside there. Now I rotate that triangle inside the cube, and it shuttles back and forth, goes to the left side. It's coming from the lower right up towards the upper left corner. I'm sorry that you can't see all those pictures, but it's a very beautiful thing. So we made a model. Next picture, we have a model where you can see I made just such a frame so you can literally see the triangle shuttle back and forth. Next picture. Here we made a steel cube. Could you block my head out? We have a steel cube, and it is made in a general chassis, a frame, and that cube is made in two halves. You can look at the right-hand side of your picture, the white cube, and you see going up in the middle of it here a groove, but there the two halves. There's a groove that goes completely around it, zigzag, 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 six parts. And the cube is mounted rigidly, and two halves apart like that, and there's an axis, two journals in the end, and there's a handle that moves a rod running through the diagonal of the cube, which is horizontal in our picture. And mounted on it near the left-hand side, you'll see a triangle, three struts coming out from the shaft to the triangle, and there's a point of that triangle sticking out at the top of the cube right now. We rotate the handle of that shaft, and we find that the triangle's end, which is up through the top of moves down the far left side. Next picture. Can you see that moving down the far side, the far top side? Next picture. It is now moved clear down to the bottom. Next picture, and it's at the far side. Now it is starting to shuttle back again. Next picture. Now this business of the triangle pumping back and forth inside happens to be nothing more than what happens if you remember that if you complete a vector equilibrium's 8 corners by putting 1/4 octahedra on them, you get a cube. Do you remember that? Okay. That being so, then this could be a cube. And if it was so, this triangle would be in the corner of that cube. Now, what happens when the big cube represented by completing those corners, that consists of eight cubes. You can make a big cube out of 8 little cubes, 2 cubes to the edge. I want you to assume that, so there'll be, for each of the 8 triangles here, there'll be 8 cubes. And this triangle in my hands is in the cube in this corner here. And when I pump this down to become the octahedron, it simply is shuttled from one side of the cube to the other. I found there was a triangle in cubes doing very strange things, so that I wanted to really study what they were doing, and found by making these models, sure enough, the triangle can rotate in the cube, but what happens is I made my triangle a little smaller than the cube, so that on each corner of the triangle, and that steel model, the frame, we had a little steel pipe running out from each of the three vertexes of the triangle, out through the runner to be guided. And we found that as it goes through the cube, it literally makes a circle, makes an arc. The end makes an arc. In other words, the end goes outwardly as it goes through and then back flush. And we made that model in such a way that those were all tubes, and we have made it so we could have lights, so that when you'd find that as you did this, on each of with the eight triangles that can be in any cube, they would all be pumping, and they'd be going two ways on the edges of the cube with the little lights. You'd see a sphere. You see a cubicle, a spherical cube. And see it being defined by shuttling lights going both ways as a consequence of the pumpability of these triangles in them. All these things have to do with experiences we have. We try to explain all kinds of phenomena absolutely just as a inventorying of data, of energy. But I'm quite confident these relate to all the different kinds of physical phenomena we do have. Next picture. But they do explain how and why, when the vector equilibrium became an octahedron, and the octahedron became a vector equilibrium, and each of the spheres became spaces, space became spheres. As they did so, each of the triangles bulged a little, so that, inasmuch as every one of them bulged in the transformation, it made the whole system bulge uniformly, all directions, so it became a spherical bulge. And this is what brought about our visibility of the electromagnetic wave. Here's something we had yesterday, the precessional effect of the two edges of the three ball edge tetrahedron, or two frequency tetrahedron, coming together precessionally. Next picture. I'm reviewing that quite rapidly because I want to get to some other things that I've added in. Next picture. Over and above what you had yesterday. They're the two halves of the three frequency. Next picture. They come together as the tetrahedron, precessionally again. Next picture. And we have then this is a 8 frequency, and they come together again as the, next picture, as the tetrahedron. And next picture, again, we then have the two 1/8 octahedra. And I'm sorry to say the top one is not clear, and they precess together to give us the cube. This is the first cube to appear in spheres. In other words, you can't have a sphere with 8 cubes, just the corners that tall. There are in this, and the base is 6 and the 7, so there are 14. So this first cube is apparently 14. It's very, very possibly something to do with carbon. It seems very logically so. Next picture. There we see the completion of the corners of the octahedron, of the vector equilibrium, by putting on the 1/8 octahedron in each corner. Next picture. Then we take it off, and we get the vector. They're the two halves of the 3 frequency. Next picture. They come together as the tetrahedron, precessionally again. Next picture. And we have then this is a 8 frequency, and they come together again as the, next picture, as the tetrahedron. And next picture, again, we then have the two 1/8 octahedra. And I'm sorry to say the top one is not clear, and they precess together to give us the cube. This is the first cube to appear in spheres. In other words, you can't have a sphere with 8 cubes, just the corners that tall. There are in this, and the base is 6 and the 7, so there are 14. So this first cube is apparently 14. It's very, very possibly something to do with carbon. It seems very logically so. Next picture. There we see the completion of the corners of the octahedron, of the vector equilibrium, by putting on the 1/8 octahedra in each corner. Next picture. Then we take it off, and we get the vector equilibrium itself. Next picture. And then we take this whole thing apart in this slicer. Next picture, please. I also then want to remind you of something I gave you the very first day at the vector equilibrium, the number of those shells, you remember. First shell 12, next shell 42, next shell 92, counting up to 146, the plus 92 gives us 238. I'd like to show you something about that I didn't mention that day, because we had the our model, our formula for the numbers of balls in the outer layer was always, remember, frequency to the second power times 10 plus 2. Remember that? And I made that very clear why that was so. So we found then that we had this layer of 12 and 42, 92, and 162, so forth, 252. Then, however, this was the first layer, but there was a ball inside. So it's zero layer. In other words, it can't be a layer, just to say, unless the ball itself really, there's a ball there, and it has an outside and an inside. And these layers have been enclosing, so I'll have to remember then, this was being frequency second power times 10 plus 2, we then found that was 10, and then we took over. So this is 12 was the number 1, the first layer. This is number 2, this is number 3, number 4. Those are the numbers that became second powered. Okay? So the center ball is 0. So I find out, remember what its formula is. So it is frequency is second power times 10 plus, so 0 to the second power is 0. Times 10 is 0. Plus 2 is 2. The value of the second in the ball there, it turns out always to be 2. Otherwise, its own concave, its own convex. And I've given you unity as 2, and you'll find it showing up time and again when we come to this extreme. So I find it a very, very exciting point, and I hadn't given it to you the first day, and it was very important to come in today. Next picture, please. Here we have the knocking the central ball out, you remember, and from the vector equilibrium, and immediately became the icosahedron. Same 12 balls, simply the squares disappeared, and they became triangulated, as the pumping model shows very, very clearly. Let's make a quick review of it. That we went from open vector equilibrium down to here. Then we add these in here, and here's icosahedron. That's icosahedron. So it's first, like everything else, a degree of contraction. Everything that happens in vector equilibrium where the realities begin to occur, there's always some degree of contraction. So this is a much further degree of contraction, even further so when it came down to the tetrahedron. Incidentally, there's another tetrahedron in the jitterbug, which I haven't tried to make for you before. Very nice one. This is a polarized one. See the precessional edges, my left hand and right hand, I have the double edges, all the rest are single. All these things occur without ever breaking the edge. Otherwise, the integrity of the system is always there. Next picture, please. On the left, you'll see these are pictures from Linus Pauling's paper, Linus Pauling's book, and you see a column there of he's got a polarized column, and he has the same picture I showed you, taking off one whole large corner of that cube. Next picture. I'm sorry, there's something else over on the other side that's very interesting. I made in the late 30s and early 40s, I was able to get a hold of beautiful little clear crystal balls, and I found it was transparent, gluing them together. I was able to make very, very fine models. I think we still have them, but they began to tell me, this upper row here, I began to really get faithfulness in respect to various atoms, and this all was part of what kept me going. You can imagine when I first began to discover all these rational relationships, and I was able really to talk about them in the 30s, and I began to confront scientists with when I was writing, and they found no identity with what they were thinking, and they were not thinking models, and they felt any attempt to bring the models in was really tending to really roll backwards into the Platonic era, and this is all nonsense. So that what I would have to say to myself, I would ask the scientists if he could find anything wrong with my arithmetic or my geometry. They'd say no. I found this beautiful hierarchy of rational values, and I'd say, do you think I ought to go on? And he would say, yeah, I think you seem to have logic in it, all right, you must well pursue it, but it doesn't have any significance in physics. It's just sort of a mathematical pastime. And so I finally had to ask myself a good question. I said, am I so important that the universe would secrete a great cul-de-sac of incredible beauty and elegance just to fool me? I said, I'm just not that important. So I have to assume it's really very important, and the other people are wrong. But this had to be my argument, and I've carried that on since it's been a really very long time. Next picture. On the left, we then see our friend the tetrahedron with the octahedron in the center. I didn't have a nice model like that to show you the first day, so I thought I'd show that again. Next picture, please. Something's gone wrong on my picture. That was going back. This is a picture of great importance because we're looking at the skeletonized tetrahedron with the octahedron inside it, and on the left-hand side, lower left-hand side, you see a blackened tetrahedron. Its base is on the table, and immediately to the right of its base is then a base of an asymmetrical tetrahedron. It has the same triangular base, both equilateral, but you see a dotted line going from the lower mid-right side of the big tetrahedron. There's a dotted line going to the top of the small tetrahedron in the left-hand corner. And that is then one of the x, y, z coordinates running, because the octahedron then has 3 corners, and this is one of the other. And that edge then makes an asymmetrical tetrahedron that's leaning leftwards and leaning to our piece, but has exactly the same size base as the tetrahedron, the regular tetrahedron on the outside. So the bases are congruent. So we know they're the same. The vertexes, top vertexes, apexes are congruent, and the bases are the same area, so their volumes must be the same. And that is a 1/4 octahedron. You see it is just exactly 1 quadrant of the octahedron if you study it carefully. So you can really feel very comfortable when I give you the octahedron as a volume of 4 and the tetrahedron as a volume, when the tetrahedron is volume 1. I'm just confirming to you from the other day the count of the tetrahedroning when instead of cubing. When instead of superscript 3, we call this then tetrahedroning instead of cubing. And there is a count for each of those layers. The one, then the two get up to 8, 27, 64 they combine. So you now feel quite content to, because we have also found that the structure is triangle and if it isn't triangulated, it's not a structure, unstable, and that the tetrahedron was then the simplest prime structural system of universe. And so when you count in tetrahedron and cube take 3, we're being more economical, and if you use a cube, you use up 3 times as much space as nature's using, because she's always most economical. So if you want to catch on what she's doing most economical, you've got to use the tetrahedron. Next picture. Again, we really can't see. There's a vector equilibrium to the right, and it shows the 8 little 1/8 octahedra. No, the 8 tetrahedra go in, and the 6 1/2. Next picture. And that's showing a completion of one of the corners of the vector equilibrium to make it the cube by 1/8 octahedron. Next picture. This now is very, very important. We haven't come to this yes, we did in the terms of spheres in packing. And let me remind you again, when we're talking spheres in packing, we're talking about vertices. And when we're talking about edges, we're talking about, when we see lines and structures, we're talking about the edges. The counts are very different. Because there's one vertex, there's 2 areas, and three edges, so we see different. We're now looking at a skeletonized tetrahedron, and the center of gravity of the tetrahedron. And we pulled out of the center, from the center of gravity of the tetrahedron, a 1/4 tetrahedron. And that 1/4 tetrahedron, you may remember, was formed by we had a triangle of closest packed spheres, and its edge read 5, its edge read 4, and there's 1 ball on top. It was a 3 frequency. There was then nestability. You remember that? Found that there was, when I had 3 balls, there was no space. There's no, at a 2 ball edge. Not we had the 3 frequency or 4 balls, did we have then? No, that gave us a ball in the center. It had to be 5 balls of 4 frequency before we get the tetrahedron, the 1/4 tetrahedron. And this then was in the hierarchy of nestabilities. In other words, it wasn't just being arbitrary and saying we're going to have 1/4 tetrahedrons and 1/8 octahedron. We found that those occurred where a ball could nest, and they were the sequence of the first time, the second time a ball could nest on top. You first nest on top to make a tetrahedron. Next time it made a 1/8 octahedron. The third time it made a 1/4 tetrahedron. Next picture. Now those 1/4 tetrahedra up at the top, I've taken an octahedron. Taking the octahedron, and sorry, on each of its 8 faces, we put a 1/4 tetrahedron. Again, it's regular equilateral triangles, all the same vector edge, so they fit perfectly well. I got one here, and then another one here. And when you do, you'll find that the apex of those 1/4 tetrahedra are in the same plane as that line between the 2. And what it does is to form the rhombic dodecahedron. It's a fascinating thing. Each one, as they come up here, this makes then for each of the 12 edges on the octahedron. These apexes come up here, and it becomes a flat here. It makes a diamond. So it makes a diamond on each edge of the octahedron. There are 12 edges, so you get 12 diamond faces, and there's your rhombic dodecahedron. A rhombic dodecahedron is a very exciting kind of a form. Its volume is exactly 6 when the tetrahedron is 1, and the octahedron, its cube is 3, and the octahedron is 4, and so forth. 6. And 6ness what is this rhombic dodecahedron? Remember, the vector equilibrium has 12 vertexes. And those 12 vertexes of the vector equilibrium are where every sphere in closest packing is contact to the next sphere. Now, there also were the spaces and the spheres in closest packing. And what the rhombic dodecahedron does, each one of those diamond faces occurs at the point of tangency. There are 12 of those diamond faces, and each one, the center of it, is where each sphere touches the other sphere. So what the rhombic dodecahedron, like the cube, fills all space. So what it is both the sphere and the space. It goes in exactly, and there's an octahedron space and a vector equilibrium space, and it exactly goes to the center of gravity of that space. So it represents the volume of the sphere and the volume of the space that belongs to that sphere. And there it is, the volume is 6. It's this beautiful rational number. Now, we're going to see a lot more about this rhombic dodecahedron because it is then really the epitome of the behavior of the spheres in closest packing, and it is, I would simply call it the domain of a sphere, and sometimes I call it a spheric, because it is the domain of the sphere. It's the sphere and the sphere's own share of space. And that it is not a 20 like the vector equilibrium, nor a 4 like the octahedron. It's a very important number. 6 is a spheric space, a domain. And we've been dealing with spheres in a way which sort of used to think about spheres and so much of the pi business. So, well, somehow there's some very nice numbers coming in here without so far getting into any calculations of that kind whatsoever. Next picture, please. Now I have a very strange cutting here where we take the vector equilibrium and we take the 1/8 octahedron that we put onto each of the triangular faces there to make it into a cube. Then you remember that the vector equilibrium has, as a sphere, it had 25 great circles. Remember that? And remember those 25 great circles. There was 3 great circles, 4 great circles, that's 7. There was 6 great circles, make 13, and there were 12 great circles, make a total of 25. If we had each one of those great circle planes were extended and into the cube, and it would, if I had those planes then come out, I've got this corner on here, and they get outside the vector equilibrium, and they cut up this little corner into pieces. Next picture, go back to the picture, may I see that picture again? So what you see there on the left, on the lower right is the 1/8 octahedron corner. And you can see the lines on the surface of it, and it's been cut up internally by all the 25 great circles. Now, back in 1947, I did my trigonometry carefully, and I found what the volumes these were, and they all come out rational number. That these little fractions are coming out rational. Boy, you better work harder still. And I just like to have that one mentioned. Next picture. Now here is looking at a vector equilibrium cut through the center, and we'll see a central vector equilibrium and 1, 2, 3, there are 4 enclosures. I found that whereas I gave you for each layer in terms of spheres, there were 12, 42, 92, and so forth. I found that the volumes were growing. The volume of the vector equilibrium is 20, and the sum total volume of the vector equilibrium is always frequency to the 3rd power times 20. For instance, if the frequency were 20, then the volume would be 3 to the 4th power. It's a very, we do not start with a 0, we start with entity. 20 is unity. Unity can never be less in vector equilibrium. Unity is 20. In the octahedron, unity is 4. It never is less. That's where the number begins. So that when I found that the rate at which layers grew of the vector equilibrium, I gave you the series of layers. If I took where the outer set of balls were occurring, between that ball and the next layer in it, there would be a plane to be struck, and that for any 2 layers, they combined to give me a very interesting number where the volumes were growing as frequency to the second power times 6 plus 2. In other words, there was something to do with this spheric space. This number 6 being very unique to the rhombic dodeca or the domain of the sphere. And so that those spaces that you're looking at there now, pairing any 2 will always be frequency to the second power times 6 plus 2. Next picture. What I'm looking at here, as lower right-hand corner, is quite difficult to see. You're looking at the icosahedron, and it is you've got the perpendicular bisectors of it. In other words, we're looking at the 15 great circles that give you 120 spaces, 120 right triangles on the surface of the sphere, which I said the Babylonians identified as very important. If I can have the picture back again, I found then that inasmuch as the octahedron has 8 faces, and there were 120 triangular faces showing there, I said, can you divide 120 by 8? And I found you could. It's 15. And I said it could be that if I took the icosahedron's face and added around each of the 3 edges, I would add, because I know there's 6 inside, the 6 triangles inside the icosahedron's face. So 6 from 15 leaves me 9. There are 3 edges. Therefore, if I could find a way of mounting 3 triangles on each edge of the icosahedron's triangle in a symmetrical way where they would make a corner of 90 degrees, like the octahedron, then I might have found an octahedron inside the icosahedron. And sure enough, we do have it. On the lower right-hand side, you'll then see the octahedron in the octahedron and the icosahedron. They skew like this. We have tomorrow. I'll bring a model here where you'll see the icosahedron inside the octahedron, and you'll find that it literally is rotatable. Will you bring that, Mehdi, from the office tomorrow? Next picture. Now, remember, I'm looking at, again, I'm not seeing enough. I'm going to go to the board to show you your squares and triangles and your counts were all perfectly clear. But we have the 2 triangles and a square. But I want to show you something about triangles and squares, which then also applies to rectilinears. That model is here? Oh, how beautiful. We will not go any further without it. Now, you recognize your yellow octahedron now and your red icosahedron. And notice it is skew in there, the points like that. And I'm going to do this. It will rotate right in there. It's fantastic. The beauty of these 2 coming together. So I want to get into really the rationality, the interrelationship of this icosahedron, which is always bothering you because its volume is 18.51, and said all the others are rational, and you have to realize it's a very special behavior, that icosahedron, because it can only have one layer of the balls in closely packing, do the contraction, no room for the second layer. In the vector equilibrium position, there is room for the layers, but when it's contracted, only room for that. The outer layer can be triangulated, you can have no more layers. It is inherently a single layer affair. So again, it makes me feel it is very much the electron behavior, and I have to note these kind of reciprocities. Now, I was going to come over to talking about, if I make any quadrangular form, but not equal edges. If I bisect those edges and interconnect, I do not get four similar forms. Not so. If I take any triangle, I bisect its edges and interconnect, I get four exactly similar triangles. That is, the triangle is inviolable in the matter of its. It can look like anything to you in this universe, but always, the countings I've been giving you always come out exactly the same, whether it looks like a regular tetrahedron or not. And the same thing, if I made that a rectilinear thing, it'd be a whole lot of trouble, as you know. So but in the tetrahedron can look like anything you want, and it still comes out this way. Now, there were two forms that showed in the last pictures where I saw they were not clear enough to really bring to your attention, but I'm now going to get into an accounting, just doing this for you myself. I'm going to make I've got a tetrahedron made of I've got rubber bands coming from me, and I'm going to hold the base of my tetrahedron between my 2 feet. This is a basic one, and you can take a hold of the vertex over there, and I'm going to make a line parallel to my feet here, and I'm going to hold this tetrahedron's top here. As long as you just move it this line, always not parallel to me, the area of the triangle it forms at the base here will be the same base and same altitude, because the lines are parallel to one another. Agree? So then I find that I can move that baseline, then I can also then move my top here in a plane parallel to the floor. So I find that out of the tetrahedron's 4 corners, I hold 2 of them. I hold one edge fixed only, and the other 5 edges are continually changing, but it always remains the same size tetrahedron. So I could move this vertex way over there. I can move that one on the floor over there. Always the same altitude, same base. Otherwise you could get to extraordinarily asymmetric looking tetrahedron here. But this always holds true. And I'm quite confident this has a whole lot to do with the fundamentals of tunings. I said I could subdivide those triangles any way you want. Doesn't make a difference at all. All comes out always the same value. I think it's a whole lot to do with electromagnetic tuning, where you can tune in here and I can tune any place in the universe. We simply come in. I haven't made that particularly clear, that point, but as time goes on, that'll clarify. Next picture, please. The first day I tried to have a stick standing up here and didn't work. So I had a picture of it here, but it doesn't really do much better. I've got two sticks standing at the lower left-hand side, and they can swerve anywhere. But then they, over the right, they fall towards each other, and so they engage each other tops. So now they can act as a hinge. Next picture. And here we have the 3 of them falling towards each other and making a tetrahedron. But its legs can go out, so we have to have a set of tensions down there. Next picture. That's part of what I've been talking about. Next picture, please, about the distortions. Here you have a drawing I was making of tetrahedra, these very simple things where they get very narrow, get to be like the tree. So I gave you the other day a tree, as we know, the cambium layer. Each year the cambium layer encloses the next one. And we find they literally do grow. The top is narrow and they are tetrahedron. They might look more like a cone to start off with, but no, you'll find the roots literally do the stresses tend to go out tetrahedrally. So that, I said, each layer of the cambium layer, the tree is continued one tetrahedron enclosing another, and the branches themselves go out as tetrahedra. And you find the wing root is really exactly that. The bottom of the wing root in here is deep, and she's flat, goes that way. That's the shape of the wing root. So each branch is a tetrahedron, and it gets its cambium layers, and each twig is the same. They continue this way with tetrahedron embracing tetrahedron. And so the bud and the whole thing comes out of it. Now, I was just making pictures here of tetrahedra, and I had them perpendicular to the Earth. There's an Earth surface with upside down at the bottom. That's all right. There's no upside down universe, so it was valid. I had been making that picture when next day somebody gave me a picture of radiolaria. Next picture. And these are radiolaria, and look just like my sketching, so much so I thought I'd like to just show these two coming together. Next picture, please. Here I have 3 ships. I was in the Navy, and I've been taught about Galileo's parallelogram of forces. And I've been taught that you had, the way you make a parallelogram of force, you have two masses moving such a velocity in such and such a direction. So you make the vectors that length, respectively. Then you make two lines parallel to them, making a parallelogram. Then they had you make a diagonal of the parallelogram to the point of impact, and then extend that diagonal outwardly right through the point, equal length to its diagonality, and it would be the resultant of the forces. Well, when I got in the Navy, I began to feel this was not very nonsense, because I said when two ships run into each other, they don't go waltzing north-northeast for 12 miles. One goes to the bottom, and that wasn't in the diagram, and I think you're going to have a little different kind of a diagram. So I found that both ships were in great acceleration. And the fact is, when they do hit, they rise because the resultant is outwardly of the Earth. They're both in acceleration, they're trying, so the total resultant is really primarily upwardly like that, and then one goes down and one rolls away over that side there, and one goes in the bottom. I found it really made the music stand for them, and really made then, I found the tetrahedron again. The three legs and the vertical of the tetrahedron. Next picture. While we're looking at such forms, I thought it'd be interesting to look at may I have that back, please? This is the looking in a cloud chamber. And I spoke to you the other day about two lines can't go through the same point at the same time. And this, when they bombard, with a neutron bombarding a whole lot of atoms, this is a typical kind of the picture, cloud chamber picture. We see these resultant angles of the bombardment. Next picture. And put all the light you can in on this, please. I spoke to you the other day about going to the island of Crete, because I could read this picture well today. I took photographs in the great palace of Knossos, and on the wall there you'll see a hexagon. This is what is called the king's sign. And why they call it the double axe, I don't know, but because I think that's a really very foolish kind of way to talk about it. Quite clearly is the hexagon. Next picture, please. And blot me out, and let's just have these pictures. This is another one. It's a little cocked, though. Next picture. And there you see the distaff side, like the cross, the English flag with the vertical cross and the diagonal cross. That's the distaff side. I just wanted to see these things that are on that wall, and I spoke to you about them, the possibility that this great invasion of breaking down of Crete, which has been the stronghold of the water people, was broken down by lesser water people who were more landed of the Ionians coming out, and suddenly the mathematics breaks into the open, but it breaks open on the distaff side with the x, y, z coordinates rather than the 60 degrees. I think, remained very, very secret to the navigator and calculator. Next picture. Here I've taken 2 of the DNA, RNA, just tetrahelix, 3 of them. And you'll find that as you make one of these, you make it spiral positive, you make it spiral negative. But you find that if you make them all positive, then they will nest in one another. But if one's positive, one negative, they do not nest. They have to be, and this is when you're twisting rope, they'll have both other positive and negative twists to settle one into the other. Now, one of the things that have been very fascinating to the Watson, Crick, Wilkerson, and all the people who have studied along with them, all the virologists trying to understand what's going on here, is that the design that is codified and controlled by the DNA RNA, we find that the child unzips from the mother as the prototype form just comes apart like that. So it has a lot to do with trying to put these things together and see how they would nest into one another and why they might let go. Now, because I also do my trigonometry in very extreme depth to be sure to really have my figures very close on, I'm really quite familiar with the form that the chemist or the biologist, the virologist making a model like this simply finds, as he did, that he had 36-degree increments to each because he found it was a helix. And so 10 times that was 360 degrees, so it seemed to be a cycle. I found it really was not exactly so, because if you take the tetrahedron, it's like cut a plane perpendicularly against this line through here, that this angle here is 70 degrees and 32 minutes. And so the octahedron, when we balance, and one sits in it, so this angle is 110 degrees, 109 degrees and 28 minutes, 70, 32. They're absolutely discrete. So I found that there was a very interesting set of information coming in where when great plates of steel are sheared and great testing of Navy work and so forth, that they always tend to shear at an angle which the metallurgist has been calling 70 and 70 and 110, which add up to 180. And so too have the faults, the earthquake faults and so forth. The earth faults continually showing up in the 70 and 110. I said, I'm sure they're not 70 and 110, they're 109 degrees and 28 minutes and 70 degrees and 32 minutes. But it makes a great deal of difference when we make sharp accounting. And I found then that when you make the tetrahelix, the tetra coming around, because there's accumulation then of the dihedral angles to come to the top. And lots of people take the tetrahedra and try to put them together edge to edge like this. And you seem to be able to get, if you were just doing it with things like this, you say, I'm getting 5 around 1. But you find this little opening there. And it's always there. So we find out exactly what that opening is. We take 5 to the 70, 32. I know I was doing something strange here. Right? Got 2, this is a 2. 252.40. So we take 360 degrees minus 352.40, and we get 4, 6 and 9 minus 2 is 7 degrees and 20 minutes. This is the difference. So that when we get in that tetrahelix going up like that, we find that the 70 degrees and 32 minutes is in there, and yet there's enough torque in my models when I make this long thing so that you can pull them together. Otherwise, in the twistability, you can get one to wind in tight enough to the hole. But they want them to spring. Now, one thing that they couldn't quite understand what they were looking, that the child wants us, tends to unzip from his mother. So here's the unzippability suddenly there. I was able to explain this to the Watson-Crick-Wilkinson group, and that has found considerable favor with virologists. That's probably so. But their model looks so strange that they don't think about it as being tetrahedral. I found human beings just not tending to think that if you really get the kind of experience you're having with me, you're going to have to always think tetrahedrally, and you realize that really all helices are really brought about. There are many ways in which you can make them by taking just strange matchboxes and other tricks and putting them together. But it always comes out following the same rules and laws. Next picture, please. This is simply a picture of the when I gave you the hammer thrower and the showing precession and why the wheel tilted the way it did. This is part of my. If any one of you would like to, you can go back and look at May 1940 Fortune magazine, and you'll find my explanation of the double spread page of the gyro, which the Sperry Company said was absolutely faithful, and they didn't think it could be done, but it was done. Next picture. Now I'm just looking at a large tetrahedron and inside of it and the octahedron and so forth. Next picture, because I'm doing some. I want you to think at a big tetrahedron now in which something else is going on. There's a center of gravity. There's a center of the base triangle. You can see that. Now, above it, there's a point, and that is the center of gravity of the tetrahedron. That's where the 1/4 tetrahedron comes into it. And above it, an equal increment there is the vertex of the 1/8 octahedron, which is superimposed. Can you get me out of the picture, like every bit we can of what we're looking at there? There is then the tetrahedron, and it encloses with the same common base, a 1/8 octahedron, and enclosed within it is a 1/4 tetrahedron. Now, a 1/8 octahedron has a volume of 2, remember? The octahedron has a volume of 4, so 1/8 turns out to be 2. And the 1/4 tetrahedron, then it has a volume of 1, where the 1/8 octahedron is 2, and the tetrahedron itself, in this case, I'm going to make it a volume of 4. If the volume of the tetrahedron is 4, the 1/8 octahedron will have a volume of 2. It has the same base as the big tetrahedron, but half the altitude. And the 1/4 tetrahedron has 1/4 the altitude, and the same base. So it is. If the big tetrahedron is 4, the small tetrahedron is 2, and the bottom one is 1. That is, the volume of a 1/8 octahedron turns out to be exactly twice the volume of the 1/4 tetrahedron. 1/8 octahedron is twice that of a 1/4 tetrahedron. Next picture, please. We're going to have some very interesting things showing up here. Now I've got 4 black 1/4 tetrahedra coming out of the big tetrahedron. Next picture. Now there's a regular 1/4 tetrahedron. As you know, the regular equilateral triangle has 3 perpendicular bisectors. I'm like taking a plane perpendicular to the base plane, three such planes, and chopping. They come down to the perpendicular bisectors, and they cut the 1/4 tetrahedron into 6 parts. Remember, if I stepped tetrahedron to have a volume of 4 for the convenience, and we made then the 1/4, 1/8 octahedron volume of 2, and we made the 1/4 tetrahedron volume of 1. I've now chopped these all up into units so that each one will be 1/6 of 1. For a moment, I'm going to multiply everything now. So each one of these blacks will be 1/24 of a tetrahedron. There were 4 faces, and it breaks in 6 parts. There's 1/24 of a tetrahedron. So I call that unity. Then the tetrahedron has 24, and all the other numbers multiply the same way. Next picture. That 1/24 of a tetrahedron is a very interesting thing, because you can make it out of one triangle. I have the dimensions there. It's not a right triangle, but it is a triangle. And so you can fold it up out of one triangle. When you fold a tetrahedron out of one triangle into a tetrahedron, then it has for instance, you can take an equilateral triangle, bisect its edges, interconnect, you get 4 triangles, and then you fold on those truncated corners, and you get. So when you do, energies that would bounce around inside of a triangle then keep bouncing around inside of the tetrahedron. So this is an asymmetrical tetrahedron that's folded out of all one triangle. Therefore, it is an energy inhibitor. It'll hold energy bouncing around inside of it. Next picture, please. Now, move my head out. You'll see the 1/4 tetrahedron, and there are, on the sides there, excuse me, we've not done this here properly, so that I'm going to ask you to go back, if you remember that black skeleton where I had a tetrahedron, and under the 8th octahedron, under it the 1/4 tetrahedron. And there were a whole lot of little lines there. I not only took this vertical plane of cleavage of the perpendicular bisectors of the 1/4 tetrahedron, but also of the 1/8 octahedron. So it too broke into 6 parts. But because the 1/8 octahedron had a volume of 2, and the tetrahedron had a 1/4 tetrahedron a volume of 1, when I took one away from the other, one is under the other, then what the difference, the space between the 1/4 tetrahedron and the 1/8 octahedron is also 1. Because its total volume is 2, and the thing enclosed is 1, so the space between them is 1. So when I then have these vertical planes cutting both the one superposed on the other, the perpendicular bisectors of the base triangle, each one breaks into 6. And the 6 ones on the next picture, I'm going to have the top ones will be gray and the bottom is going to be black. That's what you're seeing there in the lower left-hand side are the gray ones, which lay on top of the black ones. And they will fold in on top of it. And next picture, there they are. The grays are on top of the blacks. You can see them there in the lower left-hand corner. And each one, the gray is exactly the same volume as the black one. In other words, the space between the 1/4 tetrahedron and the 1/8 octahedron was equal to 1, the total volume being 2, which was the volume of the 1/4 8th octahedron. So I found then if I'm going to call then the black 1/24th, I'm going to also then let them be unity. So it should make the tetrahedron have to be 24. And then we find that each black and each gray there and each black have a volume of 1. So what you're looking at is a set of 6 sitting on top of 6. The volume of 12 involved in what you're looking at there. These are very asymmetrical. These are what I have here on the table. Here is a there's a one sixth of a quarter tetrahedron. I call that an A, and here is the sixth of the 1/8 octahedron sitting on top of it, and it's a B. They're obviously very different shapes. And we call this the A quanta module and the B quanta module because, remember, then octahedron and tetrahedron do fill all space. And when we break them up, both A and we get something common to tetrahedron and octahedron, we suddenly can make all the geometries. And the A quanta and B quanta, these two alone, complement one another to make all the geometries. So they've got to be very, very, very important. This is one of the most important of all the discoveries I ever made. I think I'd like to just pass that to you to hand around, because you've got to get a little feeling of it. And may I have the next picture? There you see two 1/4 tetrahedra fractionated, which equals 1/8 octahedron. Next picture. Now I'm making a large, you're doubling the size of a 1/8 octahedron. On the lower right-hand side, you'll see a 1/8 octahedron. And I've put 3 of those on the corners of the thing on the left to make I'm doubling the size of the 1/8 octahedron. And you see then there's that 1/8 octahedron in each corner, and then there's one sitting on top of it there. You can see 6 1/8 octahedra there, but remove those 3 top ones. Next picture, and you find that you have what was inside there was a tetrahedron. Now, this is now a new this is the 1/8 no. This is 1/4 tetrahedron doubled in size. And in order to make it, you have 3 regular 1/4 tetrahedra on the corners. And then inside them you start piling the blacks, remember now, are the A's, so there's AA and the B, AAB. But I found that space in which they are, notice that you got a 3-pointed star, haven't you, of grayness. I'm going to be able to take those A's and B's out of that space and rearrange them so they don't look like that at all, but they still fill the same space. In other words, they are reorientable within the same space. Next picture. That's way, way back. That's not the next picture there. There. Now they're the same ones, but their narrow ends are in, and they were not that way at all before. To find then, they're all radiant from the center. Did you notice? Can you go back one picture? I'd like to be able to show those two, the transformation, this one where they're radiant from the mid-edge inwardly. Their butt ends, they're putting their energies inwardly. The next picture, now they're radiant from the center out. They're radiant energy. The same phenomena, same A's will be rearrangeable in space, bring about completely different energy conditions. This began to really, really get me. And you realize if you took the center of gravity of each of those A and B's, the center of gravity is deployed in this picture. The first one they're concerned. I don't know if you've ever seen X-ray diffraction where you hit metals and so forth. You really can see these displacements taking place. Now, I'm going to talk some more about these A's and B's. And they are very, very fascinating. I found them, what I was putting together was this group right here. And they can be put together in two ways. Here's an A and an A, but the B has been put in. But here's the, well, those two are the same. That's, in this hand, I've got an A and an A, base to base, and the B is out here. But no, A and A, but they, you can put them that way, but the point is when you then turn like this, you find that they are, this is isosceles. They're isosceles in a number of different directions. This is an isosceles triangle. So that they're rotatable. They're right angle, a right angle, a right angle. Three sets of right angles in the inside here, which allow changing the right angles around, because that's an octahedral center. Realize how rotatable that is. And they're all these isosceles forms, so that they can really be changed around. Now, next thing about those A's and B's, you can go on and make all, I have, and I've made all the geometries there are, but when I handed those to you, if you look at them carefully, you'll see that there's also a little line, a curved line in there. As they come together here, would you come take this one and pass it around? This is then, this point is the center of the spheres in closest packing, and these are a sphere in closest packing. You'll see how much of some of them, part of them occur in the space, and part of them are inside the spheres. And so as they keep coming together, they continually put spheres together. Now, the next thing I discovered, which was really, I told you then, this fills all space, the rhombic dodeca. And its face, its mid-face, is at the point of tangency between the adjacent spheres in closest packing. And then I found this extraordinary thing. I can make this into an octahedron. So all those different 90 degrees, I can rotate these pieces around in an incredible number of ways. And this thing fits down into the rhombic dodecahedron here. So, this is what I call the coupler between any two spheres. It is also all space filling, just as rhombic dodecahedron. But you'll see the two spheres kissing one another in here. So its volume consists now of, each one of those is 1/24th of a tetrahedron. And there are obviously 2, 3, 6, 12, and 12. There are 24 of them, which is the same as one tetrahedron, isn't it? There are 24 of them. So it is back to Alfvén unity like the tetrahedron. And I call this thing the coupler, because and I find then what it does. Now you're going to see a series of pictures where you can rotate. You make these in different colors, the A's and B's, to see what you're getting. But the numbers of rotations in place within the coupler seem to be very close to the same number as the periodic table of the atoms. Looks like it's 92 rearrangements within it. Next picture, please. I'm just going to show you the fast. You sort of have a little feeling. Oh, there you're looking at the octahedron. One half of the octahedron is broken up into the A's and B's, the top half. At the upper right-hand end is an A, and the white is a B. The only difference between these is another unit of altitude. with the same base. As long as you have the same base and you increase 1 unit of altitude, and each is always the same fraction. So the orange then is another 1 unit more of altitude, and the black is the top of the tetrahedron. Then goes another one and another one. They're always the same increment, therefore the volumes are always the same. They get thinner and thinner and thinner. We find then energies that are putting on a conductor like this really tend to keep going, the waves going outwardly now, it gets flatter and flatter, getting more and more parallel to the conductor itself, and then trying to precess outwardly. So this is one of the problems with conductors. I want you to understand how really a wave, because this can act as an energy input, each one of those, a wave going on the conductor system. They don't have to get very much altitude there, and they seem to be absolutely parallel. Next picture, please. I'm just showing the A's and B's a little closer here. Next picture. And there we're seeing, I put together, I handed to you just a minute ago, 3 of them. And this is a negative, maybe, because it really is one's a positive, one's a negative, which way I do it. You can fill all space with a negative one. These are very extraordinary tetra, because you remember, regular tetrahedron can't fill all space, but this one can fill all space. Or the positive one, or they can do it together. And I call this, there are 2 ways of putting the 6 together, positive and negative. They can go this really long way, and the 2 ways they can go together. I call these the sight. The little one is a mite. These are the sights, and you see in the 2 different arrangements, and they fill all space. So here, if we're using a quantized unity, where tetrahedron now must be 24, and octahedron is 4 times 24, 72, so forth. But then find that these have a volume. They have a basic unit of 6 quanta. It's very interesting. That's 6 quanta, because we found that there were 6 quanta when we talked about the basic putting the proton and the neutron coming around the 2 models, and we got the 6ness of basic 6 quanta. There's 6 quanta in there, and they will fill all space, both positive and negative. So they do all the tricks you can possibly do. Next picture, please. These pictures that go on making sights and mites. Next picture. Next picture, please. Next picture. This was part of the rhombic dodecahedron. I found I could open it and fold it, putting tapes to the edges, and it all fold together again. Next picture. There's the coupler. Next picture. Now, that's the way you can make either positive or a negative. You must start with two A's, and then either B on the right side or B on the left side. Next picture. And I've identified then where the rhombic dodeca is. You can see on each vertex of the vector equilibrium, and then where the coupler occurs. Next picture. Now, there's going to be a series of these. Next picture, where you see your spheres in the center. Next picture. Next picture. Not very sharp. Next picture. These beginning to show you some of the strange combinations that begin to occur with the reds and blues. In some places they're conducting, sometimes they're not conducting, sometimes they're fortifying, sometimes they're subtracting, and so forth. Next picture. Next picture. I'm going to just keep right on, will you? Just a little flick because there are a whole series of them. Next picture. I made a series of all the possible combinations. These are all in the synergetics book. Next picture. And there's an analysis of each one, how the energy values are, what it does, way shunting, blocking, conducting, and not conducting. Next picture. Just keep it on, please. I'd like to go through the series quite rapidly. You can just do it at will. The quicker you do it, the more rhythm you get out of it. Now, I'm going to just quickly, that's the end of the A's and B's, but into some studies of the complexes of the octahedron and tetrahedron which are made. Next picture. If you look at the complex, a big vector equilibrium made of octahedron and tetrahedron, this is a two-frequency, you'll find that there are very different aspects of them. You're going to see 5 different aspects. Next picture. You see through it in quite different ways. Next picture. Next picture. Keep right on. Next. Now, keep on. Next picture, please. Just getting into when I began to find the great strength you get of such trusses. This is North Carolina State back in the early 50s. And we found that make very, very, very powerful structures. And next picture. Then we begin to get into fascinating mathematics. If you remove my head from the picture, these are octahedron, tetrahedron complex trusses made out of single sheets of paper, strips of paper that just you find that you can triangulate, and they simply coming together. Next picture. Next picture. This ones are done with a single set of wires, and so you make like bed springs and so forth. The wires can go making them. Next picture. Next picture again. That's Linus Pauling. These are out Linus Pauling's book. Next picture. You see the chemists paying great attention to these things. Next picture. Next picture. Now we're coming back to joints of the octahedron tetrahedron trusses. Since the rhombic dodeca occurs, we found that where the radii come together, these are then the perpendiculars to where all those lines that come in. This then becomes a very natural joint for it. And so you'll find a number of studies of that going on here. Next picture. There is this thing comes apart in 1, 2, these 4 parts. And may I have the picture back, please? And you can see open like that, where the faces and the perpendiculars coming in. Next picture. And here's one with clevises, and you find that all these things can be brought together. Next picture. And it was along these lines that made the truss. This is the beginning of my studies for what became the Ford Motor Company big dome. Next picture. Where we made our struts out of sheet aluminum, just angled, and we found that the angles could overlap. That around the vector equilibrium's 12 vertexes, there's a turbining. I've shown you how balls can get to 2 layers begin to turbine. So there's literally these surfaces turbine around one on top of the other. So it is possible to have them overlap and just turbine on one another. Next picture.
That's the last one. That's the last picture.
All right, very good. in the coupler that I gave you with is an octahedron, those asymmetrical octahedron. And being an octahedron has really very interesting properties of octahedron. The mathematical properties. You're used to the x, y, z coordinates, and then to the fact that if you get into cartography and so forth, you'd find that the latitude, longitude grids, anything that happens in one octant of the x, y, z coordinates, it tells all the mathematical stories, things upside down, reverse, and so forth, but they go positive and negative. But it's all the numbers, all the number relationships are all covered by your octant. I find this of great importance because I would like to really know why that is. Can I give any kind of a mathematical, geometrical proof of why that would be so? I find it really quite interesting because, as you and I know, then the tetrahedron is then the minimum system dividing universe inside and outside us, minimum structural system, and it is then has its four sides, so that there really are only to a total system really only requires four facets to tell the whole story. And I'm going to then look at an octahedron where we'll have this is a solid sheet. Then find that this is a solid sheet here. Now this is a solid sheet here. And this is a solid sheet here. So you make the octahedron with four triangles where it's single bonded instead of in the tetrahedron the four triangles are edge bonded, double bonded. And here is just a single bonding, and yet they really cover the whole story. So it goes plus minus, and that's exactly the way we get into our trigonometry and our trigonometric tables. This being a plus, this is a minus, a plus and a minus. So going around any one point. The clock you get going around a point there, looking at it, is plus, minus, and this is your straight trigonometric basis for doing everything. Now, I found it very, very interesting to get into that because then this octant, I'm able to when I was trying to find out how many different relationships existing there, this did come into play in a very big way. Now, next thing I'd like to talk about in that relationship is something that I've come to in numbers. When we do our spherical trigonometry, I'm going to talk about spherical trig a little more with you. I mentioned it quite a lot the other night, and I pointed out that when we were brought to trigonometry, we were bothered by the idea that sines and cosines, the trigonometric functions were fractions, and that the fractions were seemingly different phenomena, edges and angles. But I've shown you that if you start with wholeness, you start with the universe and system, then there are the central angles and the surface angles. And one of the things that I discovered that was fascinating is I did those great circles that showed you. Went from the 4 great circles. The angles in there, when I spun it, where you went, where a line went altitude of a triangle and altitude of a square and altitude of a triangle, it only went through 2 sets of vertices when I spun it. Where it went that the altitude of the triangle was 5444, and the altitude of the square was 70 degrees and 32 minutes, and the triangle 5444 again. We'll just look at those. Looking at the vector equilibrium. When I spun it on these 12 vertices, so there's 6 axi, this is one that went altitude of a square, and then altitude of a triangle, altitude of a triangle. Now, in doing that, we have, I said, this altitude here is 70 degrees, 32 minutes, which is an interesting number because that's also familiar with the dihedral angle of the tetrahedron. And this was 5444, and this is 5444 again, altitude of the triangle. Those numbers are interesting. If I think about 60 as being the normal angle, so let me take 60 in relation then to 5444. And that's 6, and then 5 minus 4 is 1, and 9 minus 4 is 5, and there we are, 5 degrees and 16 minutes. 2 times 5 degrees and 16 minutes would be 10 degrees and 32 minutes. So it's very interesting. 60 plus 1032 is 7032. So if I use 5 degrees and 16 minutes as a basic increment, this one is saying minus 1 plus 2. So it goes plus 2 minus 1 minus 1, plus 2 minus 1 minus 1, so it goes around. That I found very typical. And when we went then from this first phase of the vector equilibrium to where I made we got this set of the 6 great circles, which you did get from this. Let me do this in different color. When I did that, you'll find it dividing the surface of the... There was also, oh yeah, the three great circles, which are those of the cube. And the 3 great circles of the cube come about from the 3 square faces, and they do this. They never get into the triangles, they only get in the squares.